Good morning, pre-calculus. This is a resource video that will be attached to your teacher's digital session. In this video, we will cover how to create the determinant of a 3x3 matrix by hand, how to find the inverse of a 2x2 matrix by hand, how to find the inverse of a 3x3 matrix using a graphing calculator, how to solve a matrix equation, and what is an identity matrix. So let's move on. So part of this video, Miss Blankenbeckler has already gone over before, or part of this slide. So we're going to scoot down here to the bottom where we have the 3x3 matrix. Feel free to pause the video if you need to copy down the directions, but I'm going to go right into how to do this. So you have a 3x3 matrix. And so what we're going to do, it says to rewrite the first two columns to the right of the matrix. It says behind the matrix, but it's really to the right of the matrix. So these two columns are going to be rewritten over here. So we're going 1, 2, 0, -4, 0, and 3. Now we're going to multiply along the 3 down diagonals, and we will add those two numbers together. So that means to take the 1, the -4, and the -1, and we're going to multiply them. We're going to multiply. And so we have 1 times -4 times -1 is 4. And then we go down the next diagonal. 2 times 1 times 0 is 0. And 3 times 0 times 3 is also 0. So those three numbers will be added together and come up with a 4. So far we have rewritten the first two columns of the matrix. We have multiplied along the 3 down diagonals, and we've added them together. Next we're on step 3, multiply along the 3 up diagonals, and we'll add those two numbers together. So 0 times -4 times 3, that is 0. 3 times 1 times 1, that is 3. And 1 times 0 times 2 is also 0. And we're going to add those three numbers together, and we're going to get 3. So we just completed step number 3. We will now subtract the two numbers down at the bottom. 4 minus 3 to give us 1, and that is the determinant of a 3x3 matrix. All right, next slide is the inverse of a 2x2 matrix, and I'm going to add by hand. That's not very good. Let's try that again. By hand. Okay. All right, so you see this little cutout. That cutout should be available to you in your lesson resources. The inverse of a 2x2 matrix. So this is basically like one big formula. Okay. And the formula, it's kind of just it's the same formula, just kind of double it. Okay. So underneath the 1 is the determinant. Okay. And so the determinant can also be written as AB minus BC. So Miss Blankenbeckler should have covered that with you on yesterday's video. Now, this is also to say that the determinant cannot be 0. In other words, you can't have a 0 in the denominator, so therefore the determinant can't be 0. Okay? So why do we do the inverses of matrices? Well, we can't divide matrices. Okay? So we have to do the multiplication of an inverse. Some of you guys may probably associate this a little bit better with multiplying by a reciprocal. Okay, so that's why inverses exist. The symbol for a matrix is inverse is the x to the first power. -1 exponent. Sorry, I said that wrong. The -1 exponent is the symbol for the inverse of a matrix. And the matrix, in order to have an inverse, must be a square matrix. So it would have to be a 2 by 2 or a 3 by 3, etc. Okay? The inverse is undefined when the determinant is 0. So up here, where I said the determinant cannot be 0, in the event that you have a determinant that is 0, that point your answer would be not possible. So the inverse is undefined when the determinant is 0. All right, so what we want to pay attention to is this part right here. Okay, now I'll refer back to the formula in a few minutes, but how do we do that? What does the formula say? The formula says take the positions A and D, switch them, take the signs of B and C and change them. So that is what happens in the inverse formula for a matrix of 2 by 2. Right? So let's get in there and let's see what happens. So it says find the inverse if it is defined. So the first thing we need to do is we need to decide if it's defined. So we go and we find its determinant. Right? So determinant is calculated by A, B minus B, C. So that's multiplication between A, B, and B, C. So what we'll have, A is 3, D is 2, minus 4, which is C, times the B, which is 1. And so that is 6 minus 4, which is 2. So our determinant is defined, therefore we can go find its inverse. Now, inverse formula, smooth up, and hopefully you guys wrote this down right here. This is probably the better one to use. 1 over the determinant. We're going to switch A and D, change the signs of B and C. All right, so our inverse, which would be A to the negative 1, will equal 1 over the determinant. The determinant is 2. Create a matrix behind it. A and D switch, so 2 and 3 are going to change places. B and C will change signs, so it's negative 1 and negative 4. And we distribute that 1 over 2 into the 2 by 2 matrix to get our final answer for this inverse at 1, negative 1/2, negative 2, and 3/2. This is our final answer. Okay, we'll try that again down here on B. We'll do our determinant. That is 4 times 0 is 0, minus 6 times negative 3 is negative 18. Double negative gives us an 18 as a determinant. Moving into the inverse formula, 1 over the determinant. Switch some things around. 0, 4, change positions. The negative 3 and the 6 change signs. We distribute the 1/18 into the matrix. 0, 1/6, negative 1/3, and 2/9. And our final 2 by 2. Sorry for those of you that want me to show you the answer. There was the answer. Alright, so our final 2 by 2. We'll find our determinant. See if it's defined. 2 times 6. 2 times 6 is 12. Subtract 4 times 3, which is 12. That gives us a 0. Since the determinant cannot be 0 for an inverse, this is not possible. That is how you find the inverse of a 2 by 2. Alright, so next we're going to find the inverse of a 3 by 3 using a graphing calculator. Now this is the matrix, this is the 3 by 3 matrix that we used earlier to find the determinant. And we know that the determinant of this matrix was 1. And we did 4 minus 3, which was 1. So we know this exists. So if you have a graphing calculator, now would be a good time to grab that, and we will start to input this into the graphing calculator so you guys can see how to create the determinant of this 3 by 3. So, in the graphing calculator, right there, that red button, okay, just above that red button is the word matrix. Let's see if I can. Alright. So we have to hit second matrix, and we get the option here to edit. So we want to go to edit. And you can choose any matrix that you want, A, B, C, D, all the way on to I. I'm just going to go ahead and choose A. Now I'm editing this matrix, so I get to choose the dimensions of it. So right now it's a 3 by 2. I'm going to change it to a 3 by 3 by hitting 3, enter, 3, enter. And so that, enter, gives me a matrix of 3 by 3 that I can go in and change the values. To change the values, you can simply overwrite them. You can simply, our first entry is 1. So if you tap 1 and hit enter, it will override the entry that's there. So we'll keep going. 2, enter, 3, enter, 0, enter, -4. And it's important here to know to use the negative button, don't use the subtraction button. If you use subtraction, it won't work. It'll give you an error. So 1, enter, 0, enter, 3, enter, enter, make sure you hit that enter button, and -1. Alright, there we have the matrix into the calculator. At this point, we need to quit. So on top of the mode button, there is the word quit. So we want to hit second, quit, and it just takes us back to the main screen. So here in the main screen, we're going to go back to second matrix. Underneath the math tab, the second column, the math, so we'll move to the right one. The very first choice is DET. So if we were just trying to find the determinant of this matrix, we would just say, hey, let's find the determinant of the matrix A. And there you can see it's the same one that we had earlier. Okay? So now if we want to find the inverse of that matrix, you're going to choose, go back to the matrix menu, choose the matrix that you want, which is A. The -1 button, I just highlighted red. The -1 as an exponent is the symbol for the inverse of a matrix. So we hit enter, and it gives you the inverse of the matrix. So that 3 by 3 that you see in the calculator is the inverse of the matrix in number 4. Okay, so this is solving matrix equations. And since we can't divide matrices, typically when we see an equation like AX equals B, we have a tendency to want want to divide by A. Well, we can't do that, okay? So we have to multiply by an inverse. And since we just looked at how to create inverses of 2 by 2, that's where we're headed. That's what we're going to do. So we have this basic little equation that we're trying to follow. We're going to use the inverse of A and multiply it by B. So the inverse must be in front when we do the multiplication. We're going to multiply the matrices first and then distribute the scalar, which would be the determinant, okay? And so let's just kind of get in there and see where we end up, okay? So we have to find a determinant of A real quick so that we can find its inverse. So that will be 3 times 1 minus 2 times negative 5. So that is going to be 13. The inverse of A will be 1 over 13 times the rearranged matrix of A, 1, 3, 5, and negative 2. Okay, so there's your inverse. Now, it says that we're going to take x equals, we're going to use the inverse of A, and we're going to multiply it by the B matrix. And it says to multiply the matrices first, and then distribute the scalar. So notice that I did not take the 1/13 into the matrix yet. Okay, I'm going to wait to do that later. So 1/13, and then we have 1, 5, that's 5. Clean that up, sorry about that. 5, negative 2, 3, times the B matrix, 0, negative 2, 4, negative 1. So we're going to multiply the two matrices together first, and then we'll distribute the scalar. So, the multiplication of the two matrices, 1, 5 times 0, 4. 1 times 0 is 0. 5 times 4 is 20. It's 1 times negative 2. 5 times negative 1, which is negative 2 and negative 5. Be negative, where is it? Negative 7. This comes down. This comes back over. So negative 2 times 0, 3 times 4 is 12. And then negative 2 times negative 2 and 3 times negative 1 is 4 minus 3, which is 1. So that's the multiplication of the two matrices. The 1 over 13 gets brought down because we haven't used it first. So a hint here is when you distribute the scalar, the determinant becomes the denominator. And if we can reduce the fractions, we will. But we're not going to have to. So our final answer for the solving of this matrix is 20 over 13, negative 7 over 13, 12 over 13, and 1 over 13. And that is solving an equation using an inverse. Last topic in this video is using an identity matrix. Now, an identity matrix is like multiplying by 1. When you take a number, it's not the color I want it, when you take a number and you multiply it by 1, you get the same number. So this is the same as that. So in matrices terms, a identity matrix is the number 1. So if you were to multiply by an identity matrix, and these identity matrices will have a diagonal of 1, a square matrix with diagonals of 1, it's like multiplying by the number 1. It doesn't change the matrix. So when you look down at these two problems, and you notice that the original matrix, which you're starting to multiply, is equal to the exact same matrix, then you must be multiplying by 1. Now, 1 in terms of a matrix is called the identity matrix. So one of the things that we were supposed to talk about when we did multiplication of matrices is when matrices are compatible to be able to multiply. So in order for that to happen, you look at the matrices and you go, okay, this first matrix is a 2-row by 3-column matrix. Now in multiplication, these two numbers must be the same. So it has to be a 3. And since identity matrices are all square matrices, this must be a 3 by 3 identity matrix. So for number 1, this has to be 1, 0, 0, 0, 1, 0, 0, 0, 1. That is the identity matrix that would fit to work in problem number 1. As we look at problem number 2, it's going to be different because the dimensions of number 2, this is a 4-row by 2-column matrix. The matrices have to have the same dimensions in the middle in order to multiply. So this must be a 2, and since it's square, also must be a 2 by 2 matrix. So when we look at it in terms of identity matrices, it has to be a square 2 by 2 identity matrix. So therefore, is 1, 0, 0, 1, and that's the identity matrix that fits this problem.